if you got it twice. For people who have joined late. And hopefully that would be enough. If you have any questions, you can email me and I will try to answer you as soon as possible. Is there a delay to whatever I'm saying, or can you see me live? Okay, no answer, meaning I will assume that means you are seeing me live. At least I am hoping so. Okay, perfect.
Yes, I can.
Okay, perfect. Okay, so first thing first, before we start the lecture, I have received some questions by email from quite a few students. So I'll try to answer these questions so that everyone can benefit. One question I have received from multiple students has been, we have tried to join the meeting and it says asking for permission to join. If that happens, it means you are by mistake using your personal email, not your SQU email. This will give you a problem. It has to be using your SQU email. Okay. Now, at the beginning of the lecture, I do admit people, but once I am in full screen mode presentation, I cannot keep clicking on people that try to join late using their personal email. So unfortunately, they cannot join through. Okay. Another question I have received is about books. So as I said, the book we are using is called OpenStax, University Physics Volume 1. It is available online. A PDF copy has been uploaded to your Moodle. And unfortunately, we do not have physical copies of this book. So all introductory physics courses, 2101, 02, 03, 07, and 08, are moving to these digital books. We do not have physical copies. You do not have to pick up any physical copies from SQU. If you really want a physical copy, you will have to purchase it yourself. It is sold on Amazon. You go to Amazon.com, you can find it there, and they do ship to Oman. Another option there is, which is what I personally did, I went to a bookshop and I printed it. The book is about 1,000 pages, give or take, and depending on the bookshop, a page costs, the black and white page costs anywhere between 5 and 7 bezas. So that's a total of around 5 to 7 riyals, which is still cheaper than Amazon books. So that's what I did personally. I printed it for myself because I will be using it over and over again. Also, I like to scribble on my book. This lecture will be open to everyone. I have made the link accessible to section 10 and section 20. So we might have people here from section 10. Okay, if you know people there who are asking about it, I don't have a problem. We're more than happy to have people here. The only requirement is, as I said, you have to use your SQU account, otherwise there are issues. Labs and tutorials, the team is unfortunately still not confirmed. I am hoping to get the team confirmed by tomorrow, inshallah, which means we will not have a lecture before your first lab, which is on Sunday. But what I will do is I will send you a very, very detailed email of what to expect and how it's going to work out. So try that. Okay? Any other questions before we start the lecture?
No.
Okay, that's quite a few no's. We can start. Okay, so up until yesterday, we went up and finished section 1.3, which is unit conversion. We saw how we can convert from one unit to another, specifically to SI units, which make calculations a whole lot easier. Today, we're going to introduce a new concept, or at least it was new to me when I first studied physics, which is called dimensional analysis. And the idea of it is, as we said yesterday, that we have base units, basic things in physics, of which everything else is sort of derived from. We give examples of things like velocity and speed, where we take distance divided by time and we get units meters per second, which is a combination of the two basic things, meters and seconds. Now, let me try to share my screen. Present. Can you see the electronic whiteboard?
Yes, yes.
Okay.
Yes.
That's really good. Okay, so what are our base units? If we go to base quantities, okay, we have a few base quantities in physics. So base quantity, and I will write here symbol dim, and I'll explain what that is in a second. Okay. So we have length. We spoke about length yesterday. We have mass. We have time. These are the basic ones we're going to be using in this course. We also have current, thermodynamic temperature, and amount of substance, and luminous intensity. And the idea is anything can be explained in a combination of these. What are these? Well, you know length, just meters, طول, عرض, ارتفاع. Mass, how heavy something is, certain number of kilograms, grams, etc. We all know what time is. Current is a unit of electricity. Okay. Thermodynamic temperature, what is the temperature of something? Amount of substance, you might have heard the term mole and Avogadro's number in chemistry if you have done chemistry in high school. And luminous intensity is how bright something is. So if you buy a bulb, you will see that it says something watts, equivalent to X number of watts or Y number of watts. Okay, but that is actually the power of the bulb. In physics, we don't measure the intensity of something using watts. We use something called a candela. Nevertheless, the symbol for the dimension is different than the unit of something. So what's the unit of length? Meters. The SI unit of length is meters. But the symbol, the dimensional symbol we will be using for it is simply L for length. Mass, we will use M. Time, we will use T. Now for current and things, there are others. Current, we use I. Thermodynamic, we use, this is called a capital phi. Okay, amount of substance is N, and this is J. But in this course, we are mostly concerned with LMT. Okay. Now, what do these do? Okay. Say, for example, I want to know what are the dimensions of the area of something. So what is area? We know area is length times width. Yes. For a very simple thing. I'll say length times width. The dimension of area is equal to the dimension of length times the dimension of width, which is length, sorry, it's wrong, which is, this is length in meters, this is the length in meters, so it is L squared, L to the power something. Okay? And thus, the dimension of A is L squared. We call this equation dimensionally consistent. The left-hand side and the right-hand side have the same dimensions. And I'll tell you why is that important in a minute. Let's take another example. As soon as I say circle and mathematics or physics, you will remember mostly two equations. Pi r squared and 2 pi r. Now, many students seem to forget at one point or another which one is for area and which one is for circumference. Well, circumference is just a distance, so it should be in meters. And area, well, it's an area, so it is something times something. So it needs to have dimension of L squared, meter squared. Pi is just a number, so it's dimensionless. R squared is meter squared, which is the same as L squared. So we know this is for area. If we forget, this is how we remember. Same thing for 2 pi r. We do the dimension of 2 times the dimension of pi times the dimension of r. This doesn't have a dimension. This doesn't have a dimension. This has a dimension of length. So it's the circumference. Okay. Any physical quantity whatsoever can be described as something. I will just write x, where x here is the, number. Okay, and it is described in this fashion. Its units is in this fashion: L to the A, M to the B, T to the C, I to the D, phi to the F, sorry, phi to the E, N to the F, and J to the G. What do these mean? Okay, say for example, I want to look at distance. Distance is simply in meters. So I'll have 2 meters, which means L is to the power 1 meters. What are the powers of everything else? B to G. Anyone? Zero, M. Yes, 0 is correct. So everything else will be 0. So everything else will be 0. M0, T0, I0, phi 0, and 0, J0, which means anything to the power 0 is 1. So the dimension will simply be L. Unit, meters. When is this important? Well, aside from us forgetting what equations is, have you ever heard one of those jokes or things that ask you things like, what is 2 apples plus 3 oranges? Well, you have a problem of 2 apples plus 3 oranges. Noor, I do not know what this is because I did not see your screen. You will have to explain what this is to me so that I can understand. Okay. Until we get a reply, I'll continue. Okay. When is this important? We say what's 2 apples plus 3 oranges? And you can only give me one number. Okay, I can say 5, but 5 isn't really a useful number now, is it? Because 5 what? It's not 5 apples, it's not 5 oranges. What is 5? I cannot add up 2 apples and 3 oranges unless I have a meaningful way to add them. Now I can say I have 5 pieces of fruit, but now I have changed the dimensions, or I have changed or 5 pieces. Okay, The letters, no, the letters mean, they simply mean length, mass, time, things like these. They don't have any other meaning. It's not a unit, so it's not m equals meters. It's just m for mass, l for length. Okay, now we can say, Ma'ad says 5 pieces. Correct, we can say 5 pieces, but then we have changed the question because we have now said 2 pieces plus 2 pieces. So if I say 2 orange plus 3 apple equals 5 what? I cannot put anything useful here. The best I can do is say 2 pieces of fruit plus 3 pieces of fruit equals 5 pieces of fruit. Okay, whatever the unit is on one side needs to be consistent for any mathematical operation, for any physics equation to be useful whatsoever. So let's do an example to see, and it is actually a very, very useful way to know if the equation you're writing in a test, in an exam, or just generally, or even if you're doing research, is useful or not, it's correct or not. Actually, some of the biggest discoveries in physics, okay, things like, as big as Einstein stuff, have been discovered using dimensional analysis. As stupid and as simple as this sounds, it does have quite a few rather large implications. Let's do an example. I will write 2 equations, okay, and we will have to figure out if this equation makes any physics sense or not, if it's correct or not. I will write S equals ut plus half at squared, and I will write S equals ut squared plus half at, and I want to know what is which one is correct, which one is incorrect. Let's take a look at this. S is length, distance. So the dimension of S is L. U is velocity. Now, don't worry, you don't know what these equations are. Okay, we will be explaining them in later chapters. Okay, but U is velocity here, speed. So I have, actually, you know what? Let me write it a different way and then it might be easier. I have meters per second, then I just have half, so no units. This is acceleration, so meters per second squared, and second square for time. So this is length over time plus length over time squared, time and time cancel out, time and time squared cancels out. So I'm saying L equals L plus L. Everything is in terms of length. So this equation is consistent. It is correct.
Doctor?
Yes?
Do you mean by that the units should be make sense? They are
Yes.
match up?
Yes, exactly. They need to match up. The units have to match up for any equation to make physical sense. Otherwise, the equation does not make physical sense. It's just like when we said, the apples and oranges. If I try to add 2 oranges and 2 apples, there is no meaningful answer. 5 will not have a meaningful unit, 5 what? But if I say 2 pieces of fruit and 3 pieces of fruit, I'm still talking about oranges and apples. But now I have changed the unit. Instead of saying 2 oranges, I am adding numbers of fruit. So I'm saying 2 fruits plus 3 fruits equals 5 fruits. once the dimensions match, once the units match, then the equation makes sense. So the reason we're saying dimensions, not units, is because units is a way to explain dimensions. And I'll give you an example here. Actually, you gave me a very, very good thing. Now, I have done everything in this here in SI units, right? What if I don't do it in SI units? I can do it in different units. So say, for example, I can say meters equals kilometers per hour times second plus half centimeter per minute square multiplied by hour square. Now, on the face of it, this equation is not consistent. This equation is not correct because I have kilometers and hours and seconds and centimeters and minutes and خبصة. الدنيا صارت خبيصة. But what do they represent? Can I transfer? Can I switch? Can I convert kilometers to meters? Yes. Can I convert hours to seconds or seconds to hours? Yes. So can I make it consistent in terms of units? Yes. So now if I look at it in terms of dimensions, الunit هو وسيلة للتعبير آلية لوصف الدايمنشن نوع variable. Okay, so if we look at it now in terms of dimensions, this is still length, this is still length, still time, still time. Yes, it's different units of time, but I can change between units. If I multiply seconds by 3600, I will get hour, or if I divide hour by 3600, I will get seconds. But the point is they're both time. Half is just a number, it doesn't have a unit. This is still length, this is still time squared, this is still time square. And if I cancel out, I still get this and this are the same. Okay, so the units match, or more importantly, the dimensions match. Now let's try doing it here. It's the same variables, but I've changed the squares of it. So here I will have length equals, actually, let's do it just like we did it here, there. Meters equals meters per second, second square plus half meters per second square, second square. So I get L equals L over T, T squared plus, this doesn't have any dimensions, L over T squared, T squared. And, oh, sorry, not squared. This is just a single T. And what's the problem? I end up with L equals LT plus L over T, which makes 0 sense. Yeah. I have apples and oranges again. They don't match. So this equation is actually incorrect. We cannot use it. When I copied this equation from wherever I copied it from, I must have done something wrong. Okay. So far, so good. Questions? I will share these notes, by the way, the whiteboard thing, I will share them with you. Okay, let me see the messages. Break for prayer, break for lunch. Unfortunately, I can do neither, although I also want to pray and I'm also very hungry. I cannot because the rules coming from SQ are very clear. I can only give you this lecture during the timetabled hours, exactly as if we were at SQ. Okay, so I have to start at 12 and I have to end by 1:20, and I cannot do it before or after because some of you have other lectures timetabled for other times. Sorry about that.
Doctor,
أيوة.
did you save the live?
Yes, it is recorded. It is
Okay,
being recorded today.
should be online in this time or can see later?
So the regulations from SQU are the lectures are synchronous, which means that students need to be attending the lecture and asking and answering questions and doubts that they have live. I do provide recordings, although they're not mandated by SQU. I do provide recordings in case someone has a problem with their connection, someone is absent for any reason, or if you just want to go back and look at the lecture to clarify some things later on. You can look at the recording at any time you wish, but the interaction you get during this lecture, you will not get it at other times.
Okay, thank you.
Okay. واصلين section 1.4 الحين بنبدأ 1.5. Okay. If you have no questions here, let's do something. 5, 6, 7. Okay, let's do something. Let's take a 5-minute break if you want to pray. And if you can do it in 5 minutes, you are free to do so. And we can continue in about 5 minutes time. Okay. Okay, and we're back. Sorry, this took longer than 5 minutes. We continue. Okay, taqabbal Allah to those who prayed. And we move on. Okay. الحين خلصنا 1.4 عزيز وبنروح على 1.5. Okay. Estimates and Fermi calculations. What are these? Many times you need to estimate something or you want to guess something. Okay. If I ask you how long does it take to go all the way from Rui to Jami'at Sultan Qaboos, you don't really need to tell me, 36 minutes, 22 seconds, and 2 parts of a second. That's not really, okay, it's really accurate maybe, but it's not really what you need. What you need is a ballpark figure. So something like, half an hour, 40 minutes, give or take. Or many times we go something like, if there's no rush, half an hour is enough. If there's a lot of rush, sorry? If there is rush, then 45 minutes, maybe an hour. What these are called, they're called estimates or Fermi calculations, or what we call back of the envelope calculations or ballpark figures. Say, for example, you're talking to someone at a coffee shop, or you've met someone, and you want to pitch them an idea. You have an idea for an application which you think will be useful for students of SQ. Okay, maybe your lecturer is really bad at explaining Physics 1, and you want to make an app where there are much better explanations. So you need money to do that. You need money to develop an app, and you found someone. You have that someone. بالصدفة كذاك لقيتوه في الشارع، لقيتوه في الليفت. You have 30 seconds, 15 seconds to pitch him the idea or her the idea. You don't have time to go through a very detailed calculation, but you need to give them an indication of how many students roughly will be useful. Will this be useful for? So you do something very quickly like this. You go, well, look, I know SQU takes approximately 3,000 new students per year. From these students, if I say approximately 60% of them or 65% of them go to Kulliyat Almiya, then that's about 2,000 students, give or take. Okay, so 2,000 students. From these, at any given time, usually we have 3 sections of Physics 1. Each section is about 120 students, 60 students. Say we have around 300 students per semester. So 2101 and 2107, they are the same course. So say, for example, you have about 600 students per semester. Maybe half of these will find the app useful and they're ready to pay money for it. So that's about 300 students times 2 semesters, 3 semesters in the year. صيفي بالعادة, you have less number of students. So say, for example, 300, 600, and 750. So within a few seconds, you reduced a very complicated problem of how many users are going to maybe use your app to a rather very easy, quick calculation that you can do in your head. And you have arrived to a number of approximately 750 students a year will use this app and pay money for it. Yeah. So we also do these kinds of estimates in physics. We also do these kinds of estimates in physics. We do this kind of estimation in chemistry, in biology, in agriculture, and everywhere, or just generally in our life. And it's very useful skill to have, no matter what your specialty is. And we're going to try to understand the basic broad principles of how we do that. Now, there's something very, very important. When we say a Fermi calculation or a back of the envelope estimate, the word estimate does not mean guess just out of your head. Okay, you don't just throw numbers out of your head and hope maybe it's correct. That's not the way to do it. What estimation means in a physical sense, in a physics sense, in a mathematical sense, is that you use prior experience, prior pieces of knowledge, or bits and bobs of knowledge that you have to, and some sound physical reasoning to arrive at some rough idea of what the number actually is, just like the example I now gave you for the app of Physics 2101 students. So what are the ideas? The general thing is you start small, you start with things that you want, things that you know, and you build up from there. So let's go through a physical example of something that you might actually find you might want to do. Okay, say for example, you're standing in front of a building and you want to figure out, well, what's the height of this building? Now, this is not an easy question. كم ارتفاع هذا البناية? I have no idea. How am I supposed to know how many floors, how many meters high this building is? But what we can do is we can get big lengths from smaller lengths. How? Share screen. Section 1.5. Okay, let's take a look. Here is my building. It's a really, really tall building. Okay, and I want to know what is the height of my building. I have no idea. Well, let me break it down. Okay, first I'll take a look. How many floors is in my building? My building has 1, 2, 3, 4, 5 floors. I will assume all floors. This is an office building. What does it look like? Okay, it looks like an office building. All floors are equal height. Okay, I have broke the problem down from a full building to how many? To just one floor. Okay, how high is this floor? Well, you see a person standing, okay, like this. See if I have amazing drawing abilities. Okay, you see a person standing like this, straight. This person is almost a third of the height of the floor. So I will need about 3 of this person to go from bottom to top of the floor if they're standing on each other's back-to-back shoulders. Okay, this person doesn't look very tall to me, probably average height. Let's say I am about 160 centimeters. This person looks a little bit shorter than me, so I'm going to say 150 centimeters. So we have now taken it down to this is about 150 centimeters. And now, using just these very, very simple principles, I can go 150 centimeters per person times 3 people per floor times 5 floors is equal to 150 times 3 times 5. 3 times 5 is 15. 150 times 10 is 1,500. Times 5 and add, you get about 2250. Okay, so you say it is 2250 centimeters, which is approximately 22.5 meters. And just like that, you calculated the height of a building within a certain degree of reasonable accuracy without knowing anything in advance about that building, except that, okay, it looks at that it has this many floors and this person looks a bit shorter than me. And this is what I mean by we don't guess. we use prior information. This person is this high, is this tall, and we build up from it. Okay. What other things we can do? We can get areas and volumes from lengths, for example. If I want to know what is the, actually, let's go general. Areas, volumes, and masses. Okay. I actually was doing a consultation for a business a few months ago, and this business was making preforms. Now, if you don't know what a preform is, I'm about to show you. This is what your water bottles look like before they are blown. Okay. Now, if you look at the size of this, if you look at the shape, this is a weird shape. You have the screwing cap. This is a bit wider than this. It's tapered. You have extra space. And this company had a very, very simple question for me. What is what is the shape, the best shape of the box that we can use? Okay. Okay, you are allowed to have your cameras on. Actually, I would rather have your cameras on because I would rather speak to people rather than blank screens. So if someone wants to have their camera on, please let them do that. Okay. I would actually rather have people that I can see rather than speak to myself or to a camera. Okay, back to this. All right, you see each other in the lecture theater. As long as you're dressed up modestly, I don't have an issue with cameras on. Okay, so the idea with this company was, I have a very weirdly shaped product that looks pretty much something like this, and I want to know what is the size, what is the shape of the box that I need, or what is the size of the box that I need. Now, if I want to do an actual physics modeling of this problem, it would take me a very long time, and it would also be rather difficult to do. But I have a much simpler, I have a much simpler way to do it. I simply modeled this using the closest shape I know to it. I need to move this. The closest shape I know to it is a cylinder. Okay. Now, yes, there will be some extra spaces, but for a back of the envelope calculations, that is good enough. Now, I know the volume of a cylinder is pi r squared, this area, times the length. So I simply did this, and I did some very quick calculations, as in how many pieces would fit in a cube, how many pieces would fit in an octagon, how many pieces would fit in other shapes. Yeah. Okay. You can do the same with masses. Say, for example, I want to know how heavy something is. Now, I don't really know how heavy something is, but I can have a quick idea. If I put this thing, let me put it this way. Haram. This is made of steel. I have no idea how much this weighs. But if I put this in water, will it sink or will it float? Well, this will obviously sink. So I know its density is at least higher than water. I will model this as a cube. I will take this away. I'll model this as a cube, reduce some because they have a lot of air in it. And I will multiply the density by the volume to get an estimate of the mass. Okay, anyone other than Sarah has a problem with the sound?
It is clear.
Okay, let me try something. Is it any better now? I changed the microphone from the camera to the computer. Okay. So the next thing to bear in mind when we're solving problems, okay, bear in mind that we haven't actually started solving problems in physics yet. We're just talking about how to solve problems in physics and in any other subject or any other thing we do in life, is that we need to ask, whenever we have a number, whenever we have an answer, we need to ask, does this make sense? Okay. Now, I have a lot of times I see some really, really strange answers from students. And when I ask them, how is it possible that you could have written this answer? I know you, you are a very good student. You know this cannot be correct. Why did you write it? And the answer I get is, well, the calculator gave me this number. الحسابة طلعتك. As smart as calculators are, they are not infallible, and many a time a simple mistake will render our answer useless. I will never forget this. 2 years ago, I set a question in a test where we wanted to calculate the height of Jebel Shams using some physics principle that we will later learn in this course. And I will never forget, I had about 300 students at that time, but I will never forget 2 students because the answer just stuck in my head. One student wrote that the height of Jebel Shams is about, let me actually write it down for you. He wrote that the height of Jebel Shams was 1.5 times 10 to the power 36 kilometers. Another student, a girl, I remember, wrote that the height of Jebel Shams was this. So one gave me 1.5 times 10 to the power 36 kilometers, and the other gave me 9.63 times 10 to the power minus 13 micrometers. Do you see what is the problem between these two? Or what is the problem with these two answers?
Not reasonable.
It's not reasonable. Not reasonable at all. This one is much, much more than the distance between the Earth and the Sun. Actually, the distance between the Earth and the Sun is 150 times 10 to the power 6 kilometers. This one is much, much smaller than the width of a single piece of hair. Yeah. So I will never forget these two numbers because I don't care what the calculator tells you. It is very, very obvious that these two numbers are simply not realistic. Okay, you might not know what is the actual distance between Earth and the Sun, but 10 times 36 is more like, you know, Pluto, or actually even further away. I'm pretty sure it's out of our galaxy, maybe even. Okay, خارج النظام الشمسي. Okay. On the other hand, micrometer, if I don't care about the minus 13. If you have already micrometer, you know that's 10 to the minus 6. If you have a mountain that is bigger than a hair, that is smaller than a piece of hair, or, well, actually, no. You know your ruler is about, you know this is 15 centimeters. If you have a mountain that is less than this, you should know you have done something wrong in your answer. If it's less than this, it's not a mountain. It's not even a map. Okay, so always we need to look at our answers to make sure that our answer actually makes sense. If it doesn't, first I need to check my units. Okay, I need to check my units. Maybe that student didn't mean 10 to the minus 13 micrometers. Maybe she meant 10 to the minus 13 kilometers. That would actually still be small, but it would still be reasonable. Yeah. Second thing, okay, we need to check for arithmetic errors. Maybe I simply just wrote a number wrong. Maybe I made a plus, a minus. Maybe I did a multiplication, a division. Maybe I made a mistake. Third of all, even if you can't find a mistake and you know this answer cannot be true for one reason or another, there's no shame in saying this is not correct. It doesn't work out. I'm sorry. This is the number I get, but no, it doesn't work out. I'm going to write beside the answer, this number makes no sense. Okay. Now, I'll give you, actually, we only have this, so I will skip the example. Maybe I'll do it in a tutorial later on, because I want to explain the idea of significant figures, because Sunday will be your first lab, and you will learn much more about significant figures in the lab. Okay, but I want to explain what is the idea of significant figures. There are two words which are very often used interchangeably, okay, in the English language. You mean Monday? No, tutorials are on Sundays and Tuesdays. Monday and Wednesday are lectures. Okay, so depending whether you're section 21 or 22, you will have you will have, I think, your tutorial either on Sunday or on Tuesday. You master timetable. I actually don't know it off by heart, so I will do exactly what you do, not this. Okay. And FL2101. Section 21 will be on Sunday, 2:15 to 5 o'clock. And section 22 will be on Tuesday, 2:15 to 5 o'clock. Okay. Okay. So there are two words that are interchangeably used usually in the English language, which is something is accurate and something is precise. Accurate and precise are actually not the same thing, not in physics, not even in the English language, but colloquially when we use it, we usually use the two words interchangeably. Okay. Accuracy is how close a measurement is to some accepted value. Okay, so it is very important to have an accepted value to compare it to. So a standard ruler is 15 centimeters long. Okay, now I don't know how long this actual ruler is. If I bring another ruler and measure the length of this ruler, okay, and it comes to 15.1 or 14.9, okay, I can compare it to 15, okay. But if I don't know how long this ruler is, say for example, it doesn't have any of these numbers on it, okay, say this ruler doesn't have 1 to 15 on it. It's just a blank piece of metal. I cannot say how accurate it is. Okay. On the other hand, we have something called precision. Precision is how close to each other a whole bunch of measurements are. Okay, and I'm actually going to use this to draw 4 different cases. Okay. Okay. This is supposed to be a bullseye, just like this. Okay. I'm not very good at drawing. Now we have 4 cases. We have case number 1, where my dots are like this. We have case number 2, where my dots are like this. We have case number 3, where my dots are spread out like this. And we have case number 4, where my dots are spread out like this. Okay. Now let's take precision and accuracy and see what they actually mean. Okay. If something is highly precise, or if it has high precision, it means that you do the same thing 10 times, 100 times, and you will get very, very close to the same thing. Okay, the same answer, or very close to the same answer, or to the same thing. How does this work? Okay, how does this work? Let's look at these 4 cases. Okay, these 4 are very close to each other. These 4 are also very close to each other. So we have done 4 shots, and they're very, very close to each other. These are high precision. Okay. Now, on a target scale, where do you actually want the shot to land? You don't want the shot to land all the way over here. No, I want it to land in the center. Yes. So when I want it to land in the center, okay, what I want is for it to be inside here. So this is also highly accurate. This is precise, but low accuracy. What about the 2 on the right? Well, up, we have it all over the place and not even close to the center. So this is low accuracy and also low precision. Here, down in the corner, we have it. They're not actually extremely precise. They're still a bit left and right, but they're all close to where we want them to be, to what we think the correct thing is. So this, okay, this is high accuracy, but low precision. Okay. Now, how accurate we are or how precise we are depends on several factors. Okay, it depends on several factors, and these factors are usually one of 2 types. Okay, these factors are usually either systematic or random. What is the definition of accuracy and precision? Accuracy is how close a measurement is to an accepted value. So in the case of the bullseye, your accepted or your true or your correct or your best answer is you want it to be right in the center. So if all your shots are closer to that real true answer, then you're accurate. Okay. Precision is if I keep throwing one after another, after another, after another, okay, will all my results be close to each other? It doesn't matter if they are close to the real answer or to the true number. It depends if it is close to the true, it depends if it's close to the true number. So if we go back here, okay, you see high precision, high accuracy. Actually, no, look here. Look here, okay? High precision, low accuracy. It's precise, they're near to each other. It means that we have thrown 4 times and we're right beside each other. So we're very precise, but we're not accurate because the true answer, the real thing, is all the way over here, okay? On the other side, okay, if you come here, you have high accuracy. All 4 of your shots are close to where you want them to be, to the true answer, okay, to where you want them to be, to the center, but they are not precise because they're not close to each other. They are still further apart, okay? And I will give you something that might be easier to understand. Take a look at this. Imagine this is a GPS, okay? Now what you do is you turn your GPS on and off, and on and off, and on and off 4 times, okay? Now where you want to actually be is right here in the center. This is red, so it's not showing. You want to be right in the center, exactly. This is where is the location you want to go, okay? This is the location you want to go to. Now, on the left, you have high accuracy, low precision. Because remember, definition of accuracy is it close to where you actually want it to be? So if my restaurant is in the center, yes, it's not rather precise. It's giving me marra hina, marra hina, marra hina, but they're all close to the restaurant. Okay. And you have low accuracy and high precision. Sorry, what?
Slide doesn't show on the screen.
What doesn't show on the screen?
Your slides.
Oh, the slides are not showing.
Yeah.
This is not fun. Can you see it now?
Yes, no.
Okay. Okay. So
Yes, we can.
on the left, say your restaurant is rather here in the center. Okay, I'm doing this so that you can see where it is because my pen is red and this is red. Okay, your whatever you want to go is right here in the center. Now the system on the left every single time will give you a location that is close to the restaurant, but not always next to each other. مرة فوق المطعم, مرة تحت المطعم, مرة يمين, مرة شمال. This is highly accurate. It is getting you close to where you want to be, okay, but it's not precise. On the other hand, your restaurant here is still in the center, but you have an issue where you have 4 different readings very close to each other. So every time you ask the GPS, where is the restaurant? It will give you the exact same location, but that location is not actually accurate because the restaurant على بعد شارعين من هنا. Okay, so it depends really what do you want for your application. Do you want ideally you will want something highly accurate and highly precise, but that is not always possible. Okay, now problems with accuracy and problems with the preciseness are either systematic or random. Okay. Systematic are things that we really cannot do much about unless we solve the problem itself. Random, we can use statistical methods or other methods to reduce it to a certain extent. Okay, I think we are at the end of our time. It's 1:20. Now, in your lab, you will actually speak about You will speak about things called decimal points and significant figures. You're free to leave if you want. I'm going to speak for about 2 more minutes. If you want to leave, you're free to do so. Okay. In your lab, you will speak about accuracy, precision, but to a less extent. You are going to talk about something called uncertainty. We are going to speak about something called significant figures, which will be very, very important as we progress into the course and as you move on to higher level courses and in life in general. And at the beginning of next lecture, inshallah, we will speak very briefly and very quickly about the strategy of solving problems. How do we solve problems? Not how do we solve a specific problem, but in general, when we have problems in physics, how do we solve the problems? How do we approach these problems? Okay. Thank you very much. If you have any questions, we can speak about it at the beginning of next lecture in labs, in tutorials, and otherwise. Please read your email when we send the email telling you about labs and tutorials details. Okay, have a great day.